Okay, so in this particular lecture, we are going to study the axiomatic approach to numbers. Okay, the axiomatic approach to numbers. So in our high school maths, we are already, you know, very much accustomed with the concept of principle of mathematical induction. The principle of mathematical induction, where we usually prove a statement which is actually true for all natural numbers, right? And what we do is basically we prove the statement for some base case, that is for some least number possible. The number must be a natural number obviously, and then we assume it to be true for some kth number, and we show that it is also true for the k plus 1th number, right? So I'm just giving it here, that what we do, we have a base case where we prove the statement for some least natural number, for some least natural number, and then we have the induction hypothesis, where we assume the statement to be true for some kth natural number, for some kth natural number, and prove it to be true for the k plus 1th natural number. Okay, so this is our basic principle of mathematical induction. This is also called the first principle of mathematical induction. There is also the second principle of mathematical induction, where actually the base case involves proving the statement to be true for all the natural numbers till k. Okay, this is what we actually do. In base case, we actually prove that the statement is true, or show that the statement is true for all the natural numbers till k, and under induction hypothesis, obviously, we check it to be true for k plus 1th natural number. Okay, now the question is that how is this principle of mathematical induction built up? Okay, that is, why do we use these two steps to solve to prove some particular statement for all possible natural numbers, right? Now, so basically the thing is that this principle of mathematical induction is this might be based on some some base on which the construction of natural numbers is done. That is the issue here, right? The principle of mathematical induction, which we have used a lot, that might be based on some base of the construction of natural numbers. Okay, so we are actually gonna discuss the construction of natural numbers. How is it actually constructed? How is this number system built up? And that is gonna be the topic of this lecture. Okay, so let's see. Okay, so okay, so there is a very famous quote that I'm writing it here. That is, God created the natural numbers. That is, God created the natural numbers, and every other is built by us. Okay, I don't remember whose quote this was. Okay, now the reason behind this quote is very simple, that we actually don't know when the natural numbers was actually built. Okay, but we just have a sort of assumptions in our mind, or rather reasoning in our mind that how it might have been built. Okay, so we're going to discuss that only. So there are a set of specific things which actually have helped in building these natural number system, and we call those statements to be axioms. Okay, so basically, this sort of a topic is often termed as the axiomatic approach to numbers. Specifically, in this case, we are talking about the natural numbers. Okay, we have actually, extended the properties of natural numbers to create every other number system we have, whether be it complex numbers, real numbers, rational numbers, irrational numbers, negative integers. Okay, actually, the properties obeyed by all these number system are actually extended from the properties obeyed by the natural numbers. So natural numbers, you can think it to be the base of all the other number system. Okay, so what is meant by axiomatic approach? So axiomatic approach basically means that approaching approaching something something on the basis of axioms, on the basis of axioms. Now, what are axioms? So axioms are simply some statements. Axioms are simply some statements which are naturally true, which are naturally true. We do not need a proof for these statements. They are naturally true. They are stated as such. Okay. For example, for us, or rather for a high school student, let's say, we know 1 plus 1 is 2, right? And intuitively, this is a natural definition. 1 plus 1 must be 2, right? So you can think this of an axiom at this moment. This is actually a result of the axiomatic approach to numbers, but for this moment, for an understanding, this is an axiom which is naturally true, which does not need a proof. Are you getting it? I'm not saying this is an axiom, but this is just an example to understand what axiom actually means. Okay. Okay. So 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 what are the axioms behind constructing the natural number? So that is actually we are gonna build up today. Okay. So the first thing under axiomatic approach to numbers is understanding axioms. Okay. Okay. So how are axioms important? So I hope you people have already understood why axioms are important, because till now whatever I have said, this actually means that axioms have basically helped in building the mathematical theory, because every other mathematics, it just revolves around the concept of numbers, right? It just revolves around the number system, and axioms are the starting point of any mathematical theory. Axioms are the starting point of any mathematical theory. So they are basically the the starting point of whatever mathematics we are studying today. Is this clear? Is this clear? So now let us start with axiomatizing the natural numbers. Okay, so axiomatizing the natural numbers. So it basically means that now we are going to start with understanding, or constructing the axioms, create the natural number system. Okay, so the first is the notion of equality. The notion of equality. Okay, so what equality actually means? See, before going to deeper details, let me first say a few things. See, whatever we have, like 1, 2, 3, then with the symbols equal to, greater than, less than, which you all people have already seen. Now see, these are merely symbols, right? these are merely symbols. We have attached a meaning to them, a significance to them. Is it clear? It seems it seems pretty confusing, but the thing is that these actually are merely symbols, and conventionally they have been used for some certain significance, and so we have actually constructed a meaning in our mind when we see these symbols. Okay, so when we will be studying this particular topic, we will start with them being considered as symbols and we will attach a meaning to them. Okay, so what is the notion of equality? So equality, as we already know, it basically means something is same as something. Okay, something is same as something, something is identical to something. That is basically what equality we know actually, and we use the symbol that is also pretty much known to every one of you. This, okay, so what is the notion of equality? um, I hope you people already know what an equivalence relation is, right? What an equivalence relation is. Okay, so equivalence relation is basically a mapping, in A cross A. Okay, let us leave this particular approach because it won't be at the base level anymore. Okay, so notion of equality. So under the notion of equality, we build our first axiom 1. Okay, so here we say that for all x in the set of natural numbers, we use this symbol to denote the set of all natural numbers if it exists. We say it like this, that if it exists. Okay, so if the set of natural numbers exist, and if x is a natural number, then x equals to x. Okay, okay, that is, every natural number is identical to itself, every natural number is equal to itself. Okay, this is also called the symmetry axiom. This is also called the symmetry axiom. Okay, then we move on to our axiom number 2, that is, for all xy natural numbers, so if there exist two such natural numbers, then x equal to y implies y equal to x. That is, if there exist two natural numbers and x is equal to y, then y is also equal to x. This is also called the, okay, so this is called the reflexive axiom. I'm sorry, this is called the reflexive axiom, and this is called the symmetric axiom. This is called the symmetric axiom. Okay, and then we move on to our axiom number 3, that we say that for all x, y, z in natural numbers, if x equal to y and y equal to z, then x is equal to z, and this is called the transitive axiom. This is called the transitive axiom. Okay, so these three are the most basic axioms we have regarding equality, and this equality is is no doubt one of the most important notions we have in our mathematical theory. Okay, so is it clear? Okay, and now since we already have built up the notion of equality, then we finally build our axiom number 4, which says that for all x and y, if x is a natural number and x is equal to y, then y is a natural number. Right? That is, if some number is equal to a natural number, then that number is also a natural number. Okay? Is it clear? So now we have our most basic 4 axioms, and now we will be building the actual construction of natural numbers, which we call as the Peano axioms. Okay, which we call as the Peano axioms. Peano axioms. Okay. Now, how is the Peano axiom actually built? So to understand the Peano axiom, you must have a basic knowledge of what a function is, what a mapping is. I'm not going to discuss that here at this moment, but I hope you people already know what a function or a mapping is. Now, to construct natural numbers, we actually need the help of what we call a successor function. What we call a successor function. And this successor function is needed to be an injective function. Injective function, or what we call a 1-1 function. Okay. So using this function, we will be able to generate the whole set of natural number which we actually know. Okay. Okay. So let us start with it. So the first axiom under Peano axiom is that 0 is a natural number. Okay. 0 is a natural number. Now what is 0? 0 is a symbol to signify emptiness or signify nullness, voidness. Okay. 0 means nothing. Also 0 means something. It seems pretty confusing. I'm just building up this confusion a bit more. That is, if S has the 0 element, then it is a non-empty set, though 0 means null value or nothing. Okay. So please, just think about it for a bit. It might seem to be interesting. Okay. So 0 is a natural number. In alternate versions of natural number, we have also, excluded 0 from it. We have started the construction of natural number using 1. But in this particular topic, we are constructing 0 to be inside the natural numbers. Okay. Okay. So this is pretty basic. So now, under axiom 6, we build what we call the successor function. So if x is natural numbers, then s of x is also in natural numbers, where s of x is the successor of x. Is the successor of x. Now we are at this moment, we are not defining the function. We are just using it as a symbol to denote the successor of x. Now intuitively, Sx is actually x plus 1 for all x, and we will be approaching this definition a bit later. But at this moment, Sx just means the successor of x. Okay, is it clear? Now why can't we define plus or this function at this moment? Because we have not actually developed the notion of addition here. When we will develop the notion of addition, we will be understanding Sx as x plus 1. Is it clear? Okay. So now you people can actually hold it in mind that Sx means x plus 1. So now we move on to our axiom number 7. So axiom number 7 means for all natural numbers x, Sx cannot be 0. Okay. Now this is pretty much intuitive, because the successor of any natural number cannot be 0, because this function is taking every number to the next number, and 0 is the least element, 0 is behind every number. So any successor of any number can never be 0. Is it clear? Is it clear? Also, can we do one thing? Can we define 1? Can we define 1 to be the successor of 0? Obviously we can. Okay. See, we are merely using 0, 1 as symbols here. We have not attached any meaning to them. We have not attached any meaning to them. We are just assigning elements to a set. We are just assigning elements to a set, and those elements have the symbols 1, 0, and so on and so forth. Okay. Okay. So why have I actually written this? So I mean that since 0 is in natural numbers, so what I actually mean, since 0 is in natural numbers, so s of 0 must also be in natural numbers. So we define s of 0 is in 1, as 1, sorry, as 1. Okay. So therefore, the natural numbers have at least two elements, 0 and 1. So my question is that can we, just take only 0 and 1 to be natural numbers, and we claim that there are no more natural numbers, only 0 and 1. Can we do so? Can we do so? Now, if so happens, we have already said that the Peano axioms have constructed the natural numbers. So it must be obeyed by every natural number possible. That means 0 and 1 both must obey the Peano axiom. That means 0 and 1 both must have an image under the successor function. Now there are only two such functions, and S0 is 1. So that means S1 must be 0. But this is not possible. We have already said that the successor of any natural number cannot be 0. That means there must be more to it. So now, since S of 1 cannot be 0, but S of 1 is in N, so we define S of 1 as 2. So we define S of 1 as 2. Is it clear? Is it clear? Now one more question must arise, that can't we define S of 1 as 1? But this is not possible because we actually need to make this successor function to be an injective one, which we have already just described above. S of 1 must be, sorry, the function S must be an injective function, that every image of the successor function must be an unique one. Is it okay? So now we have one more element in the set of natural numbers, which is 2, which is the successor of 1, and using this notion we can now say that repeating this process, now we can claim that whether the set of natural number has only 3 elements, 0, 1 and 2, and then we will again reach this abstraction. So we need to add another element which will define the successor of 2, which we will name as 3, and so on. So the natural numbers seem to be constructed of 0, successor of 0, successor of the successor of 0, successor of the successor of the successor of 0, and so on, right? Which we specifically define as 0, 1, 2, 3 and so on. Okay. Now is the notion of equality obeyed here? We will come to that later. Okay. Now one more axiom we have here is that for all natural numbers xy, if the successor of x equals the successor of y, if the successor of x is the successor of y, then x must be equal to y. Okay. If the successor of x equals to the successor of y, then x must be equal to y. And this is actually what we mean by injectivity, right? Or the one-oneness of a function. So it is pretty much trivial. Okay. Okay. So is it clear? So we have come to two specific things here, that we have attached numerals or numerical symbols to the images of each of the successor of zeros. Okay, and the symbols are 1, 2 and 3. Okay, so from here it is pretty much obvious that this particular set 0, 1, 2, 3 and so on, this must be contained in whatever the set of natural numbers must be, right? So the notion of equality is still not defined here. The notion of equality is still not defined here. What we have actually approached is that all possible successors of 0, repeated successor, iterated successors of 0, the set containing them is actually contained in whatever the set of natural numbers can be. Okay. So now our question is that can the set of natural numbers contain more elements than whatever we have here? Okay. That is, our claim is that can the natural numbers have more elements, rather other elements than the iterated successors of 0. So we take n to be 0, 1, 2 and so on, union A and B. So A and B are symbols other than the which actually have the meaning other than the iterated successors of 0. Okay. So the successor function is defined as we have defined it for this particular case, and here we have S of A as B and S of B as A. Okay. So the successor function is pretty much defined here, right? It is pretty much defined in this case. So now what? So see, now our main focus is to think about this part of AB, right? This part of AB. Now, can such a set, or rather, I mean that is this a final set of natural numbers? Okay. Now, to finalize the construction of natural numbers, we have one more axiom and the final axiom left, which we call as the inductive axiom. Which we call as the inductive axiom. So, what does the inductive axiom say? So, the set V is called an inductive axiom if the following conditions are satisfied. Number 1, 0 is in V. Number 2, if x is in V, then S of x is in V. Okay. This axiom is also often called the axiom of induction, and this is the axiom which we actually use in the concept of principle of mathematical induction. Okay. Now see. Now, so this inductive axiom leads us to the final construction of the natural numbers, that is, if V is an inductive set, then the set of all natural numbers must be contained in V. Okay. You can call it the axiom 8. I hope this is axiom 8. Okay. Now see. Now the whatever axioms we have studied till now, that basically ensures that the set 0, 1, 2 is contained in it. Now, is this an inductive set? This is obviously an inductive set. So if this is an inductive set, then from here, from this axiom, we can say the natural numbers is contained in 0, 1, 2 and so on. So a set is contained in a natural number. A natural number is contained in the set. So what that basically means? That basically means that the set of natural numbers is exactly equal to the set of all the iterative successors of 0. And we have completed the construction of what we call the natural numbers. Okay. So now we have only two things left to us: defining axiomatic arithmetic of natural numbers. Okay. So now we have only two things left. That is constructing the arithmetic of natural numbers. What we call the axiomatic arithmetic of natural numbers. Okay. So we have only two of them. That is addition and multiplication. What we call addition and what we call multiplication. So the addition of axiomatic arithmetic. Okay. So the first of them is addition. Okay. So how do we actually define addition axiomatically? So we have two cases. That is, number one is any natural number plus 0 is the natural number itself. And number two is a plus the successor of b is defined as the successor of a plus b for all a, b in natural numbers. Is it clear? So this is the way in which we define addition for the set of natural numbers. Is it clear? For example, what is 1 plus 2? So can we write 1 plus 2 as 1 plus successor of 1? So this is basically successor of 1 plus 1, which is basically successor of 2, which is basically 3. Now how can we define successor of 2? Sorry, how can we define 1 plus 1 is 2? So 1 plus 1 can be written as 1 plus successor of 0, which is successor of 1 plus 0, which is successor of 1, which is 2. Now how is 1 plus 0 1? 1 plus 0 is 1 by this axiom. Okay. So we have successfully built up the axioms of addition in case of natural numbers, and we already know how much important addition is in case of any mathematical theory. Okay. Now addition and multiplication, they touch every single aspect of our academic lives, right? Okay. So the Peano axioms and the successor function, this actually obeys us to define what arithmetic addition actually means. Okay, is it clear? So similarly, we build up the concept of, okay, one more thing we have successfully defined here is that this definition of addition is actually pretty recursive. Okay, adding two natural numbers actually depends on the previous numbers, right? Because see, here adding 1 plus 2 defines the is dependent on the addition of 1 plus 1, which is again dependent on the addition of 1 plus 0. Okay, so for any two natural numbers this recursively happens, right? So now we in a similar fashion we define what we call multiplication. So the axioms related to multiplication, number one is that for all natural numbers a dot 0 is 0, and number two, a dot sb, dot is the symbol for multiplication, a dot sb is given as a plus a dot b. Is it clear? Now for example, what is 2 into 3? So 2 into 3 can be written as 2 into successor of 2. 2 into successor of 2. So we can define it as 2 plus a into b. 2 plus 2 into 2, which is 6. Right? Now what is 2 into 2? Now 2 into 2 must be 4, so that we can write this. Now what is 2 into 2? So 2 into 2 is 2 into successor of 1, which is again 2 plus 2 into 1, right? 2 plus 2 into 1, that is 4. Now how can we define 2 into 1? So 2 into 1 can be defined as 2 into successor of 0. 2 into successor of 0, which is basically 2 plus 2 into 0, and we have already have the axiom anything into 0 is 0, so this is basically equals to. Is it clear? Okay. So this is how we have built the arithmetical operations on natural numbers axiomatically. Now we move on to the now so basically now I claim that we have actually understood the concept of natural numbers pretty well by axiomatically constructing it. Okay. So now we move on to the next most important property regarding natural numbers, which is actually very useful in mathematical theory, which we call as the well ordering principle, which we call as the well ordering principle. Okay. It is also an axiom itself in case of natural numbers. So what does the well ordering principle say? So it says that every non-empty set of non-negative integers. So what are non-negative integers? Non-negative integer is the natural number that we just constructed. Okay, non-negative integers, actually sometimes we use the term non-negative integers because in most of the cases natural numbers do not include zero, while non-negative integers obviously include zero. Okay, so non-negative integers, or in this case we can say it as natural numbers only, has a has a has a smallest element, has a smallest element. Every non-empty set of natural numbers has a smallest element. Okay, now is this true for negative integers? This won't be true for negative integers because if we take a non-empty set of negative integers, it can be -3, -2, -1, and it is continued here, right? So it is a non-empty set. Will it have a least element? No, because it extends to infinity, and every number, in this particular part of this set is less than -3, and they are repeatedly less, right? -5 is less than -4, then -6 is less than -5, so they're repeatedly less. Okay, so since this extends to infinity, we cannot say that it has a least element, it has a smallest element. Can we say this for real numbers? Obviously not. The same thing happens here also, because real numbers also contain all the non-negative integers. Can we say this for this set of positive rationals, non-negative rationals? So my claim is that, can we say the well ordering principle is in the positive rationals? The positive rationals. So how are the positive rationals actually built? Let this be written as Q plus. So Q plus is actually the set of all the elements P over Q, such that P belongs to natural numbers and Q belongs to natural numbers except the element 0, because we cannot define a division with 0. Now if P belongs to natural numbers and Q belongs to natural numbers, then the well ordering principle is obeyed by P and Q, right? That means, sorry, since the well ordering principle is obeyed in natural numbers, so we can always take a least element P and a least element Q, right? We can always take a least element P and a least element Q. So if we take the least element P and the least element Q, then the fraction P over Q automatically becomes the least fraction in Q plus. Automatically becomes the least fraction in Q plus. Okay, so is it understood? Is it understood? Now, why is this well ordering principle important? Okay, so I think you people have already studied this particular question, that prove that root 2 is irrational. Prove that root 2 is irrational. And how we used to do it? We used to take root 2 to be of the form P over Q. That is, we assumed root 2 to be rational, and P over Q is the least possible fraction of root 2. Then we used to deduce, then we used to come to the fact that P and Q have a common factor, If it has a common factor, then then P can be written as some R times S and Q can be written as some L times S, S being the common factor. And by the concept of division, R must be less than P, L must be less than P. So P over Q can be reduced to R over L. P over Q can be reduced to R over L. And R over L is a lesser fraction than P over Q. So our initial assumption that P over Q is the least possible fractional representation of root 2 is not true. We reach a contradiction and we say root 2 cannot be rational, therefore root 2 must be an irrational number. Okay. So how can we claim that P over Q must be the least possible fractional representation? So the reason behind it is the well ordering principle. The reason behind it is the well ordering principle. Every fraction is finitely reducible. Every fraction is finitely reducible because at some point it will reach its least possible state. Every positive fraction okay, every positive fraction is finitely reducible. Is it clear? Can't we say it about the negative fractions? We can also say it about the negative fractions, because when we are attaching the natural numbers and in the numerator and denominator, the concept of negation, the concept of negative is simply felt as the product of -1 to it. Minus P over Q is nothing but -1 times P over Q, and so P over Q naturally becomes a positive fraction, so it is finitely reducible. Is it clear? Is it clear? Now, this well ordering principle actually helps us in quite a number of proofs. Okay. Like the the proofs we used to do in case of the concept of the principle of mathematical induction is actually brought by the concept of well ordering principle. Okay, it is actually indirectly approached by the well ordering principle only. So now I just want to give a template for well ordering proof. So write it down. Template for well ordering proofs. Okay. So this basically helps us in proving some statement Pn to be true, that is Pn holds for all n in natural numbers. Pn is a statement. Pn is any possible statement. Okay. So how can we set up the steps? Okay. So step number 1: define the set C of counter examples to P being true. Specifically define C to be the set of all natural numbers such that not Pn, that is the negation of Pn, is true. There is a symbol of not. Not means negation. Negation means whatever Pn is, we negate it. That is, if Pn is suppose say Pn is this statement. Pn is this statement that 2 divides n. What will the negation of it? 2 does not divide. Okay. So the negation of Pn is true. Okay. 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 I'm also giving you a definition here, a notation rather. N bar Qn. This actually means the set of all n such that Qn holds. Okay. Okay. So this is step number one, to set counter examples, mean all those examples which negate Pn. Okay. Number two. Number two is assume for proof by contradiction. Assume for proof by contradiction that C is non-empty. That is, we assume C to be non-empty and then we reach a contradiction. Contradiction means a statement which is not mathematically true, depending which actually depends on the assumption taken. Okay. Number three. Now, how do we reach this assumption? How do we reach this contradiction basically? So by the well ordering principle, there exists a least element n in C, because C is a set of natural numbers. Number four, reach a contradiction, somehow, often by showing that Pn is actually true. Pn is actually true, or by showing that there exists a number lesser than n in C. Okay. 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 So by the step 4, what we can do is that we can conclude that C is empty, or rather C must be empty, which proves the statement, P of n for all n. Yeah, rather, let us keep it till P of n. So I am proving a very important statement regarding natural numbers in this case using the well ordering principle, and I will be giving an exercise also. So the example number one. Okay, so there is a theorem, a very famous theorem. It says that every positive integer greater than 1 can be factored as a product of primes. I'm giving the exercise here only, that is 1 plus 2 plus 3 and so on till n is n into n plus 1 over 2. Now we have actually proved this using principle of mathematical induction. Do try to prove it using the well ordering principle. Okay, then we will be able to find the relation between well ordering principle and the principle of mathematical induction. So I'm proving the first statement here. Okay, so let C be the set of all such elements m in natural numbers such that m cannot be factored into primes, into product of primes. Okay, now what can we do from here? See, now this C must have a least element. Okay, now this C must have a least element because we assume C to be non-empty. Now assume C to be non-empty. Okay, so if C is non-empty, there exists a least element, which implies there exists a least element n in C By the well ordering principle. By the well ordering principle. Sorry. By the well ordering principle. Now, now, n cannot be a prime number, right? If n cannot be a prime number, because every prime number is a, a prime numbers are product of themselves, right? What is p1? P1 can be factored into p1. It is pretty trivial. Okay, it cannot be a prime number because a prime by itself is considered a product of primes. A prime by itself is considered a product of primes of length 1. So n cannot be a prime number because prime numbers cannot be in C. Okay. Now, if n is not a prime number, by what is the definition of prime number? It is the numbers which are the product of 1 and the prime number itself. So, if n is not a prime number, that implies n is product of two numbers a and b. Let me not use this symbol. So, n is the product of ab such that one is less than a and b are less than n. Okay. Now, since a and b are less than n, that implies a and b cannot be in C because n is the least element to be in C. Now, if a and b are not in C, then a is a product of primes, say p1, p2 till pk, and b is also a product of primes, say q1, q2 till ql, because they are not in C. If they are not in C, that means they are product of primes. So what does this mean? So this means n is equals to p1, p2 till pk into q1, q2 till ql. So what does this mean? This means n is indeed a product of primes. Now if n is a product of primes, so that means, so if n is a product, that means n cannot belong to C. So if n cannot belong to C, so that basically means our assumption is false. Our assumption is false, which leads us to a contradiction and which proves our statement. Okay. Okay, so I hope you people have understood this particular lecture. So do try the exercise and we will meet you. I'll meet you guys in the next lecture.